Can everybody hear me okay? Okay. So my name is Justin Harms. I'm going to talk to you today about the next generation hyperspectral field goniometer. It's called the goniometer of the Rochester Institute of Technology version 2, or what I'll refer to as RIT. I'd also like to point out that it's not only been efforts on my part, there's been others included in this effort in various aspects, but I wanted to point them out as well, and they'll listed on the bottom of the slide for your reference. So what I'll talk about is, what is a goniometer? To those not, completely, fluent in remote sensing terminology, it might not seem like an instrument that you've ever heard of. I'll go over that. I'll talk about what we currently have, basically kind of start where a chip left off with what features we currently have in our grid goniometer. Then I'll talk about the next generation goniometer, which is the RIT. And I'll talk about the improvements that we kind of made with that device over the old one, and I'll talk about some of the new features that device has over others that we've seen out in literature. And then I'll go over the current status with you and show you some cool pictures. So what is a goniometer? Well, it's a term that we use to describe a device that measures reflected light at various angles with the goal of creating a reflectance function. So essentially what we're trying to do is measure the reflected light at every point over a hemisphere over the top of a certain target. So there's various ways of doing that. You see our current grid here doing it in pretty rough conditions. You see something similar to what Dr. Bachman had talked about before with doing it in laboratory conditions. Others like something like this. So you can move the illumination source and the sensor at the same time around the target itself. And ultimately you're trying to come up with something like this, as you saw in the last presentation. So there's various types of them. Many of them were created for specific scientific applications, because if you're trying to measure tall vegetation, you're not going to be able to use a small goniometer to do that. You're going to have to build something larger. Or if you're trying to measure snow very accurately, or if you need something that's extremely lightweight because you're going to go stomp around in the marsh. So some of them that have been built for the laboratory are very fancy, intricate designs, such as this one here. It actually uses a 6-axis robot to measure and manipulate a sensor over the top of a certain target. This one over here is a very popular system. That's the dual-view FIGO system from the University of Zurich. And it's very large and has been used for agricultural things. You see it measuring snow there. There's others here that are only measuring one plane at a time, so they don't actually measure the entire hemisphere, but they'll just do a few slices in order to keep the system very, very lightweight. And then you see others over here, like the Manta system, that are exceptionally lightweight and made to basically be broken down and put into a backpack. Our device is made to measure sediments primarily, and we want to be able to hit every single point in the hemisphere. So we're trying to get something that will create a full-featured BRDF, if you will, with azimuth rotations, maybe at 30 or 15 degrees. So this is what you saw from the previous presentation, and I just wanted to hit on a couple things as well. The IMUs and stuff like that we have on here provide us with very good information about where we are in the world. That's important because not every goniometer has those kind of things on board. They often understand the angles that they report are oftentimes from what they've told the system to do. So in zenith or azimuth, they'll command their system to go to 15 degrees off of nadir or something like that, but they don't actually often measure what it really achieved. There's other things going on here, like mechanical deflections and possible motor slippage, that can ultimately create errors in your data and make it very difficult to interpret certain terminologies. So this is a great start in that we are already starting to do motor movements and then check those with IMUs and with differential GPS antennas. But we wanted to go one step further with the next system. So the future goniometer of RIT had a few things that it needed to do. Like I said, we started with improvements, and then from there we actually use that as a springboard to go into even new features as time permitted. So ultimately what we're trying to get is a purpose-driven design that balances weight and source of error, optical and mechanical accuracies to achieve a high-performance system in a very small package, something that we can take out in the middle of the desert, that we can pull behind an ATV, miles off of the nearest paved road. A lot of those things are very difficult for larger goniometer systems that are full-featured, and you might not be able to get a 6-foot or 8-foot tall system 3 miles into the California desert, as we've done with ours. So mobility was key. We wanted a system that was more mobile. So in order to do that, we needed to reduce weight. Dr. Bachman had talked about how the original grit was a prototype that was put together in just a couple months, basically, when he had first arrived here for a field experiment that they needed to conduct. That's great, but ultimately it means that a lot of the things were off-the-shelf components because they needed to do it very quickly. And so a lot of it was steel, things that they could just find in your local hardware store or just quickly get online. With RIT, we were trying to make sure that we were using aluminum to provide excellent structural rigidity, but removing the majority of the weight. And then we're using high-performance industrial parts. And that's key because when you start talking about mobility, the first thing that happens is you want to go off miles into the desert, right? And you have blowing sand, you have austere conditions, temperatures well over 100 degrees. Those are things that can be catastrophic for robotic systems. And when you're doing that, you don't want to have a lot of downtime. So you want to design your system around this mobility that you've now created. And along with that comes the need to adapt to various terrains. If you get out there, you might encounter dune systems, something that's not perfectly level. Typically, when goniometer systems measure targets, the targets are roughly level, and you can measure the target very easily. With the next generation device, we require automatic leveling and the ability to accommodate various target heights. If we want to hug the side of a dune and measure the BRDF of that, because we're doing calibration for NASA, we need to be sure that the system is going to be level, stay planted, so that we have a common reference plane within the overhead sensors. And then also be able to accommodate the actual height of the target below the frame. So it's something that is fairly difficult to do, but necessary for us. We also wanted something that was more accurate, both mechanically and optically. So mechanically might not seem like that big of a deal, but again, if you put this in the context of very high temperatures, blowing sand, sometimes torrential downpours that happen when you don't expect because you're on the coast somewhere, or wind, it can become a big issue. So what we did to understand our position all the time is have the motor movements like normal, but we also had sealed encoders that actually are monitoring the true reached angle, so you know where the device actually ended up, which is really important. So if you moved over to 45 degrees off nadir and the wind's blowing slightly and you actually only made it to 43, we know that with the system because we have encoders that are constantly monitoring that. In addition, optically, as the two presenters before me kind of explained, there's a need to compensate for varying illumination both temporally and spatially. So one of the things we decided we had to do was compensate for this background illumination. And in order to do that, we had to gather spatially resolved illumination data. And I'll talk about that more in just a second. Another improvement that was important over the previous design was something that was fully automated. We had a semi-automated device in grid, but what we were really looking for was something that would be beginner-friendly and would be more of a set-it-and-forget-it type thing. You program your scan pattern in. The scan pattern is then executed automatically via computer-controlled motions that are constantly monitoring for errors and other things, and controlling the ASDs, all in conjunction. In order to do that, you had to have a trustworthy design, because we didn't want multiple operators to have to sit there and monitor it and ensure that it's reaching where it's supposed to be going. So we put reliable motions, we required reliable motions in austere environments. As you see here, that's water from basically a small pond that we're sitting at the very edge of. So that mud and stuff can really put a damper on your remote sensing day if your motors get gummed up. In order to achieve these reliable motions, we went with components, industrial components that are created for high ops tempo, manufacturing environments, and that's something RIT has been using. We also, as I mentioned, have error reporting for each instrument on there. So including the ASDs, we accept all the errors that they can possibly provide, and then we have error reporting from all of our other instruments that are monitoring mechanical motions to make sure that we are fully aware of everything that's going on. If it didn't reach its commanded motion, we know where it actually ended up, and we know how to handle that afterwards. So the next thing are the new features. So this is a big one. That's why it's first. Target tracking is really important, and it might seem a little obvious at first, but a lot of goniometers have a very difficult time with this because they're typically made out of circles, right? So we have circular frames that basically have a set target plane. So right here you notice that the target plane of this notional device is set, and it's exactly at the bottom frame. It can't be moved. What that means is if you have unlevel terrain or something, where your target's actually down here, you actually end up staring through your target plane and looking at other portions of the ground. You're not actually tracking a single place anymore. That raises some serious concerns about spatial uniformity of your test site. If you're on a beach or something where the tide is coming in and there's only narrow bands of a certain type of sediment you're trying to measure, that can become a big issue. And you'll end up creating a BRDF that's actually a conglomerate of other sediments that are around it. And essentially it's some synthetic reflectance function that actually doesn't represent anything. So with this device, we track a single spot on the ground, and at all times we'll always be sure to be looking at that particular spot, no matter the height of the target. That's something we measure with lasers. Dual beam design. So it's very perfect timing for Dr. Curtis to come here and talk about this dual spectrometer approach, because this is something we're interested in as well. So Dr. Bachman talked to you about how he uses the dual spectrometer approach to monitor temporal changes in illumination. It's really important because, as you've seen, cirrus clouds and moisture content and other things can really create sharp spikes in your spectra and essentially erroneous reflectance. However, there's another aspect of it that you must also pay attention to when you're doing BRDF measurements either near tall trees or near structures, and that's the spatial aspect of the illumination. So not only do you need to monitor the temporal illumination, you need to monitor the spatial illumination around it. So what we've done is we've essentially used two ASD field spec 4 spectrometers to monitor this. And one of them stares down at the target, as you see here. The other one is staring exactly opposite, back up at the sky. And over the course of the scan, we'll build up an illumination profile that is spatially resolved, in addition to the spectrometer that Dr. Bachman typically runs, which is monitoring temporal changes. So now you have that temporal and that spatial information that you need to get back to actually gathering true BRDF, or a very close approximation to BRDF. I say a close approximation because goniometers typically measure HCRF, which is hemispherical illumination, and a conical reflection back to some finite elements detector size. It's important to notice the distinction there, because when you get down to actually using that reflectance function that you've created to do other things, you have to realize that that spatial illumination is inherent in your data. So if you don't have the exact same sky conditions that you had, or illumination conditions that you have when that BRDF was taken, you're getting errors that are being passed through your reflectance function. You might not realize it, because you can't remove that diffuse information, and it has to be represented exactly in order for it to be right. So we are able to actually remove that by capturing the spatial information, and we don't have to rely on atmospheric modeling to do that, which can introduce another error in there. This is a similar approach to what's been done with dual view FIGOs from the University of Zurich. And it uses, I won't go into the details of math too much, but it uses a technique that was described by Martinchik in 1994. And again, it's similar to what's been used on dual view FIGOs. It's based on splitting the reflected radiance into a diffuse component and a direct component, and you operate on them separately. And you iterate through this, and then you ultimately will create a reflectance function that aligns with the reflected radiance that you saw from your spectrometer, and you end up with BRF, which can be converted to BRDF just through a scalar. So another important feature of this is the elevation model. We capture a digital elevation model of the target area. And it's great because it also allows us to do the target tracking, but more importantly, from that information, if we are on an incline or if our target is rotated in some way, it allows us to back that geometry back into the data. If you think about it, when you're putting a goniometer over the top of a target, the goniometer is level. If the target is unlevel, you're actually not looking at that 45-degree look that you thought you were. You're looking maybe closer to 50 or 55. That's something that this digital elevation model will allow us to incorporate back into the data. And this is all, in essence, of keeping true angles with respect to the target. That's the purpose of the goniometer, true angles. We don't care what the goniometer is doing with respect to its own frame. We care about what it is with respect to our target. And that's why we have this ability to do a digital elevation model with 2 millimeter accuracy. And we can do it for a predefined area of interest. This is just a notional concept of how it works, but you can change the sizing and the density of that. Another feature is the elevation model. The elevation model allows for the study of macroscopic surface roughness. So something that Dr. Bachman is interested in with these rates of transfer models is also understanding the macroscopic roughness. If you're measuring the BRDF of gravel or something like that, the height of those objects can induce shadows in certain directions that can adjust the reflected information, reflected light, and change your BRDF. And since a lot of our sites exhibit this large-scale roughness, we wanted to be able to actually describe it with this DPN. We can do that down to, like I said, about 2 millimeters or so. Another one is reduction of self-shading. So we have an open arc design on the new one. This is actually a picture or a model of the new one here. And no stationary overhead structure. Unlike a typical goniometer, which might operate something like this, if your sun is in line with your structure, you'll actually shadow your target almost the entire time. And that limits your information about the opposition effect. Ours was designed such that we can point the system towards the sun by having the open portion of the arc towards it, so our frame will never shadow. The only thing that's overhead is this small arm, which actually is pointing the sensor the whole time. And so you'll be able to get very close to opposition effect, about within 2 degrees or so. And you're not shadowed during any other portion of the scan. So only when you get very near to the sun could you ever actually have a shadow. Other than that, all the shadows will be behind the system. So again, that's what we don't want. What we're trying to get is something where we have minimized shadowing and allows us to interrogate the backscatter of the hotspot. So in order to do this, it's been pretty difficult, but we've basically gone to precision engineered components. Everything we've done from a custom standpoint has been modeled using finite element analysis. So not only are we understanding, are we careful of our choice of motors and things like that, and coders to make sure they're sealed and going to operate in all conditions, we also understand the deflections that we're going to see on the system via this finite element analysis. And from this, we were able to design our own frame that was made here in Rochester at a company called Trident Precision, which does a lot of precision optical designs. So even though this ring is approximately 1 meter across, its concentricity is down to 200 micron, which means we have excellent pointing capabilities versus other goniometers. And that basically, trickled all the way down to even the smallest components to make sure that the rigidity was increased, trying to improve the accuracy for suboptimal terrain. If the system has to level or something on other terrain, we want to make sure that it's rigid enough to keep its own shape, and therefore it's consistent. So again, all of our components were custom manufactured out of aluminum. The system has been assembled now, so it's sitting upstairs on the 3rd floor. It's mechanically operational. We can do all of the motions that I've talked to you about here that allow us to have these great features like target tracking and digital elevation model. What we're working on now is finalizing the control software for the device. So the high-level GUI that the user will actually use is going to control the ASD sensors and the goniometer itself. And that's being finalized right now. Our low-level control software that actually does all the motions and calculations is already finalized and is currently being tested. The next step for us is to install the 2 ASD spectrometers and then apply the final coatings, which will be avian black paint because of its low reflectance over the veneer and sphere, which is where we're operating with our field spec 4 spectrometers. And then we'll begin the testing and calibration effort after that. So, in conclusion, this is what I told you about today. Key features being the things on the new goniometer that we're doing: more mobile, more accurate, fully automated, target tracking, dual view design, elevation model, reduction of self-shading. So do you have any questions for me? Yeah, go ahead.
I have a question. So it's really cool how you redesigned the new print device, but my question is, when you have it out in the field, you don't have the ability to sort of place it on an optical table, and as your separate motors are swinging it around, you have shake in the device itself. I know the device is rigid in and of itself.
That's right.
On the ground.
Absolutely.
How do you calibrate for that?
Yes, so that's an important point, and that was one that has actually been brought up before by some of the faculty, is also while you're leveling or while the system is taking the measurement, how you compensate for any settling that may happen. And that's something we're still thinking about. From the shaking and stuff like that with our stepper motors, what we've done is purchased fully integrated motors that actually have acceleration and deceleration profiles. So we can use those profiles to create nice smooth motions that limit that vibration throughout the system. The settling from just motion of the device itself while it's taking a scan is an interesting problem. What we believe we're going to do is make sure that the system always remains level. So if the system does settle after a motion, we're going to re-achieve level. And at least that way our reference plane is correct. We don't suspect that we'll have too much lateral shifting problems because of something I didn't talk about in the way the feet are designed. They actually have a spike that goes into the ground and holds it and plants it. So if you're on a slope or something like that, those spikes will be holding the system from wanting to slide down. But yeah, the leveling could cause, we could have settling issues that affect the leveling system, and that's something we're going to have to work out. We want to make sure we keep a consistent reference plane. It's very important. Okay, thank you.